Hello, my name is Jeet Patel, and today I will present my project titled Tuning PID Controllers using TD3, RL for Nonlinear Systems. This work is part of the IE 415 course on control of autonomous systems under the guidance of Professor Sujay Kadam. My motivation for this project comes from my interest in machine learning and reinforcement learning. MATLAB's reinforcement learning on-ramp gave me a great introduction to these ideas. I wanted to use them in a real project by combining reinforcement learning with PID control to handle challenges in nonlinear systems. PID controllers are widely used in control systems because of their simplicity and robustness. They consist of proportional, integral, and derivative actions. However, tuning PID controllers for nonlinear systems is challenging due to issues like dynamic changes and nonlinearity. Using reinforcement learning, specifically the TD3 algorithm, introduces adaptability, automation, and optimal control to overcome these challenges. The objective of this project is to compare reinforcement learning-based PID tuning with conventional tuning methods. I used the TD3 algorithm to train a PID controller for a nonlinear mass spring damper system and evaluated its performance through simulations. The system used is a mass spring damper system, described by the equation. It models dynamic systems like car suspensions. The control objective is to achieve stable performance with minimal overshoot and fast settling by tuning the PID parameters using the TD3 RL agent. Let's take a closer look at reinforcement learning overview at the key components of reinforcement learning, which are essential to understanding how this process works. First, we have the agent. The agent is essentially the decision maker. Its job is to learn how to make the best decisions to control a system by interacting with its environment. Next, we have the environment. This is the system or process that the agent interacts with. For example, in our project, the environment is the mass spring damper system, which the agent tries to control. Then there's the policy. This defines the probability of selecting a specific action based on the current state and the rewards received. Think of it as the agent's strategy for choosing the best possible action in any given situation. The state represents the current condition of the system. For instance, in our case, the state might include details like the position and velocity of the mass. Now, let's talk about action. The action is a control input that the agent applies to influence the environment. In our example, this could be the force applied to the mass to achieve a desired outcome. Finally, we have the reward. The reward is a feedback signal that guides the agent's learning process. It tells the agent how desirable its actions are, helping it improve its decisions over time. Together, these components create a continuous loop where the agent learns to adapt and optimize control for better performance. The TD3 algorithm was developed to address issues in the DDPG algorithm. DDPG suffers from overestimation bias, where Q values are inaccurately high, leading to poor policy learning. Additionally, DDPG often faces numerical instability during training, which can result in suboptimal control policies, as you can see in the graph. The replay buffer stores past experiences and allows the agent to sample them randomly during training. This breaks the temporal correlation between samples, improving stability and convergence. It also enables the agent to learn from diverse experiences, accelerating the training process. TD3 incorporates three key techniques to overcome these issues. First is clipped double Q learning. Uses two Q networks and updates based on the minimum, reducing overestimation bias. Second is target policy smoothing. Adds noise to actions in the target network, improving stability. And third is delayed policy and target updates. Updates the policy and target networks less frequently to ensure more stable learning. In this project, the simulation is based on a nonlinear mass spring damper system. The system was implemented in Simulink with three key components. First is observation block. This block provides feedback to the TD3 agent by outputting the PID parameters KP, KI, KD. Second is reward block. The reward function incentivizes the agent to minimize overshoot and stabilize at the target. Positive rewards are given for staying close to the set point, while overshooting or undershooting results in penalties. And third one is RL agent block. The TD3 agent interacts with the environment by adjusting the control force to optimize system performance. The training process involved running 500 episodes with a mini batch size of 128 and a discount factor of 0.97. The hyperparameters were fine-tuned based on insights from the research paper to ensure effective learning. The reward function plays a crucial role in guiding the agent during training. It acts like a teacher, providing feedback based on the agent's performance. For example, it penalizes overshooting when the agent goes too far beyond the target with a large negative reward. This is similar to what happens in PID control, where overshoot is a common challenge if the gains are not tuned correctly. It also provides small penalties for weak control, where the agent doesn't apply enough force to reach or maintain the target efficiently. In PID systems, weak control might look like sluggish responses, where the system takes too long to stabilize. On the other hand, the reward function encourages good behavior by rewarding the agent for maintaining the target set point. This is the ideal control scenario we aim for, where the system balances accuracy and stability. Similarly, in a well-tuned PID controller, the system quickly reaches the target without overshooting or excessive oscillations. By balancing these rewards and penalties, the agent learns to perform like an optimized control system, combining the precision of PID with adaptability to dynamic environments. Now, let's move on to the results. For conventional PID tuning, this graph shows the response of the mass spring damper system with a conventionally tuned PID controller. While it achieves stability, it suffers from noticeable overshoot and slower settling times. For RL-tuned PID controller, here, the RL-tuned PID controller demonstrates significant improvement over 23 trails. The TD3 agent effectively reduces overshoot, speeds up settling, and maintains smooth control transitions. And it is consistent with step input as well. In trail 23, these results show the benefits of RL-based tuning for nonlinear systems. Now, let's compare the performance of RL-tuned PID controllers with conventional PID tuning using our experimental observations. Here are the key comparison points. First is overshoot. RL-tuned controllers demonstrate significantly less overshoot compared to conventional PID methods. Second is settling time. The RL-tuned controllers achieve faster settling times, helping the system stabilize much quicker. And third one is adaptability. RL-tuned controllers adapt dynamically to changing system conditions, something conventional tuning struggles with. The advantages of using TD3 in dynamic environments are also noteworthy. Reduced overestimation bias, which ensures more accurate control actions. Stable policy updates, making the system behave predictably even under disturbances. Smooth control, allowing for a more natural system response without abrupt actions. Here, I've included dynamic visual examples to illustrate these points. First pair of images. On the left, you see a spring with a car being thrown onto a platform. The conventional PID controller causes oscillations as the system struggles to stabilize. On the right, the RL-tuned controller settles the system quickly and without oscillations, achieving precise control. Second pair of images. These simulations use Simscape. The first GIF on the left shows a mass spring system controlled by a conventional PID controller. Notice the oscillations that occur before the system stabilizes. On the right, the RL-tuned PID controller handles the same system. The response is smooth, with no oscillations, and the mass settles directly at the target position. These examples highlight how RL-based tuning offers both faster convergence and better performance in terms of stability and smoothness. In conclusion, RL-tuned PID controllers represent a significant improvement over conventional PID tuning methods. They provide superior control, especially in dynamic environments with nonlinearities. The integration of the TD3 reinforcement learning algorithm makes the system more adaptable, precise, and robust. This work shows how reinforcement learning can improve control systems, making them smarter and more efficient for engineering applications. Thank you for your time and attention.